sheaves. Wow. Okay. Thank you, Stephen, and the organizers. Though I don't know who else is organizing for inviting me to give this talk. I think this is supposed to be like a conversation between symplectic and algebraic geometers, but in reality, I'm an arithmetic geometer, so I made the talk as topological as possible. But anyway, I think monodromy is something that most people are interested in, either differential geometry or topology or symplectic geometry. I don't know, maybe in all forms. So let me. I'm going to start with some maybe motivation in history. So let me start with the settings. Setting will be, so X for me, for this talk, again, this is not necessary, and usually people have been working more arbitrary fields, but for the purposes of this talk, X will be, just some variety over the complex numbers. And so this will be for me the derived category of constructible sheaves on X. And if this, okay, if you're uncomfortable with this, then you can just think of local systems on X, for instance. It's an example. But in any case, any constructible sheaf, I mean, this is just recalling in case, I don't know if I should recall it or not, but constructible sheaf F on X by definition is a sheaf so that there is a stratification of the underlying topological space, so that the restriction of F to the strata, which I'm denoting by xi, is a locally constant sheaf. Is a locally constant sheaf of finite dimensional vector spaces. And as far as the base field, it could be any algebraically closed. If you want, you can just say finite, you can take this to be finite dimensional complex vector spaces. Okay, sorry, I'll stop. Yeah. Okay, so X is an algebraic variety, and this is the derived category of constructible sheaves on and as are smooth. And let me assume also that pi is proper and smooth. But the classical result that if I have map of, so I just have a smooth proper morphism of complex manifolds. If you have a smooth proper morphism of complex manifolds, it just means I have a proper submersion. And if you have a proper submersion, then it's known by Hirschman's lemma that any such thing is a topological fibration. So it's a fiber bundle topologically, which means that if you look at the higher direct images of the constant local system on X, so this will be a sheaf on S in principle, but it turns out to be actually a local system because this is a fiber bundle in this case. So this is a local system. Now, local systems are characterized by the fundamental group. So this is a classical result. And I'm gonna not be precise, but the category of local systems on S is equivalent to the category of representations of the fundamental group. I'm gonna not write the base point. There's a base point. I'm just not gonna bother with it. Okay, just to remove notation. So there is an equivalence of categories between categories of local systems. Any local system gives you a representation of the fundamental group, and vice versa. If you have a representation of a fundamental group, you get a local system. And I won't go through this equivalence of categories, but roughly, if you have a local system like this, you can, so if I have S and I have a local system on S, then how do you get a representation of the fundamental group? So this is sort of the usual theory of parallel transport, but explicitly, if you're given a loop, say I have a loop in the base, then I can pull back the local system to the closed interval. And so pulling back a local system is again a local system. So this is a local system on this, but this is simply connected. So any local system is actually, it's just constant. Any locally constant thing is constant on a simply connected topological space. So it means that given a loop, if I look at the stock of this at some point, this is a finite dimensional complex vector space. Because it was whatever the rank is here. There's a local system of rank n, locally it looks like this. So the stock is just C to the n. And I have an action of loops on this because I can restrict it to 0 and I can restrict it to 1, and they're both isomorphic because restricted to 0, 1 is just constant. And so this loop, which is here based on X, let's say, will give you an action, will give you an endomorphism of Lx, which is what people call the monodromy transformation. Okay. And so you do this for all loops, it only depends on the homotopy class of the loop. You end up getting a representation of the fundamental group. Let me write like this. At some chosen stock. And again, it doesn't really matter what you choose here, but so this is one direction. You can also go in the other direction, but I won't. It actually sets up an equivalence of categories. And usually, so this is what people call the monodromy representation. This is the monodromy representation of this local system on S. So in particular, in this geometric setup, there's a natural local system, namely the higher direct images of the constant one on X. And since it's a local system in this setup, this gives me a representation of the fundamental group, and I can ask about the monodromy of this family, by which I simply mean the monodromy of this local system. Okay. So this local system, the stocks are kind of easy to characterize. I mean, why you would care about that is because if you compute the stock of this at a point, it's actually just the cohomology of the fiber. So that's what it's parameterizing. So this local system is parameterizing the cohomology of the fibers, and you're looking at how the loops are acting as you move around the cohomology. Okay. So this gives you a representation of the fundamental group of S into GLF of some fiber. All the fibers, remember, this is a fiber bundle, so all the fibers have the same cohomology. So, I mean, topologically, they're all identified. So, of course, not complex algebraic, but okay. So this is usually what's called the global monodromy representation. And now I could sort of fix my attention at a loop. So if I have, say, a disk, a punctured disk mapping into S, I could pull everything back to the punctured disk. And I could look at the resulting representation of the punctured disk. on the same homology, but now the fiber will be, this S will be some point in this small disk. I'll drop the coefficients for a second. And of course, well, this is a canonical generator, just a counterclockwise loop around the origin. The fundamental group of this is just Z, and it's got a canonical generator. And so this is completely determined by the action of this. And this is called the local monodromy. So I'm concentrating around maybe some point in a compactification of S and a disk around that point, which is such that when I remove the point, it's lying in my original space. Okay. And so a natural question is, what are the, well, one way to describe this is to kind of write down its eigenvalues. What are the eigenvalues of this monodromy operator? And so eigenvalues. So the classical local monodromy theorem says that they're actually quasi-unipotent. Well, the operator is quasi-unipotent, which is equivalent to saying that all the eigenvalues turn out to be roots of unity. This is sort of maybe the first. So this is usually what people call the local monodromy theorem. And I'll make some remarks and some historical remarks on it. But the one way to state it is if I have a map from X to S, where S is a curve, and I fix a point in the curve, and I remove the point, and I look at some small disk around that point. So this is some small disk around that point in the curve. I'm going to assume it's a smooth curve. So, and suppose that this is the general way to say it is as follows. So I have this map, and I'm going to assume that away from this point, it's smooth. I mean, it always is. I mean, so I'm going to relax the smoothness assumption here. But if I have a morphism like this, where the base is a curve, and I fix a point, and I take a small disk around that point, this is a complex curve. So there's some local coordinate, and I have some small disk around that point, then, and I restrict this morphism to the disk. If I choose a small enough disk, then I mean, it's just Sart's theorem. This is smooth over an open dense subset in here. So this is going to be an isolated singular point. So in the punctured disk, if I remove this, I assume that the disk is centered at this point. In the punctured disk, over the punctured disk, it's smooth. So I can restrict it to the punctured disk, and I get this morphism, and then I'm in that setup over there. Okay. You don't actually have to assume properness, but I mean, if you want, you can. And for the general result, you don't need to. And in this context, it turns out that the higher direct images, as long as I choose the disk to be small enough, the higher direct images of this map will still be local systems on this disk. And I can ask what the monodromy is. So again, that means I have a representation of the fundamental group of this punctured disk. And so I can ask for the eigenvalues of monodromy. And the theorem says that the eigenvalues of T are roots of unity. Sometimes people state this as follows. This is equivalent to saying that T is quasi-unipotent, which means that there are some integers, let's say n and k, so that T raised to the n minus the identity raised to the k is 0. Right? Anyway, any T like this you can write as, if you remember some linear algebraic group theory, it can be written as a semi-simple thing times a unipotent thing. And what this is really saying is that the semi-simple thing is forced to be of finite order. I mean, it's of this form. The Jordan decomposition. You can always write it as a semi-simple matrix times a unipotent one. And so quasi-unipotent means that this part still is finite order. Okay. So its eigenvalues are roots of unity. So
is there like a two-sentence reason for that you give at the level that you're talking?
Kari, say that again. Is there a
Short reasons why that's true?
Why this is true? I want to discuss some motivation in history. Let me discuss some history. Yeah, why should it be true? It's such a general thing, right? Like, where is it coming from? Why is it? and it's interesting because local monodromy is quasi-uniform, but global monodromy usually semi-simple. It's like the exact opposite. So if you start taking all these local generators, which are all unipotent, you could end up with something that's actually semi-simple. I mean, like for instance, take SL2Z, right? I mean, it's generated by Z2 star Z3. So you have two finite order things. And the local generators are both quasi-unipotent, and that happens. I mean, SL2Z appears as a monodromy group for some degenerations. Actually, degenerate elliptic curves, and you'll get things. But so yeah, so where does the quasi-unipotence come from? So the history is really interesting. So I don't know who proved it first, because depending on who you ask, you get different answers. The first thing that I can find published is, of course, due to Grothendieck, and it's often attributed to Grothendieck. So, so there are a lot of names associated to it, and I think the common ones are Riskorn, Clemens, Griffiths, Landsman. I should write Grothendieck first, and Landsman, and these two, I don't know if I can find in print. This is the first one that I see in print. Clemens's paper is there, but it appears after Grothendieck's. Grothendieck's is the most general, in the sense that he would work with arbitrary schemes over arbitrary fields, and he would work with étale cohomology, and it would be a statement, you know, saying that the analog of this would be action of inertia is quasi-uniform. But the person who studied this kind of stuff, I mean, it goes back to a question of Milner, actually. So, where he studies singularities of hypersurface terms. So Milner looked at things like isolated complex analytic germs. So germs of analytic functions with isolated singularity at the origin. And in this setup, he was studying what we now call vanishing cycles, or the cohomology of the Milner fiber. So what he showed was, so this is like this continuation of Morse theory, but in this setup, you can define something called so if you set things up, so for a small enough epsilon, I can look at the epsilon ball around the origin here. And so for epsilon small enough, and delta much smaller than epsilon, you can look at the cohomologies of what people call the Milner fiber, which is by definition, looking at the small disk of radius delta here, and then taking a point here, a general point in here, looking at the inverse image of that and intersecting it with this ball. As you vary the T in the disk, this forms a fibration. This is a fiber bundle. It's not obvious. This is what people call the Milner fibration. It's the theorem of Milner. And so in particular, you have something moving around the disk, and this is a fiber bundle. So this is a local system, and it has a monodromy action. And Miller studied the monodromy like this, and he did many computations, and he conjectured that, well, he didn't conjecture, he asked if it's always quasi-uniform. Now you might ask, what does this have to do with this kind of setup? And the two are intimately related. And if there's time, yeah, later on, maybe I'll explain how you go back. This is kind of this is the local situation. Local, not in the sense of local monodromy, but local in the sense of vanishing cycle. Like geometrically, it's the local picture. This kind of family, after doing some geometry, the local picture often ends up looking like this. And I'll try to explain that. And so, that's where it comes from. Yeah. So maybe I'll say why, maybe some more kind of, this talk was fun for me because I didn't know any history. So giving a talk like this is always fun because you get to learn about history, which, I always thought that Grothendieck was the one. I mean, the proof that I learned was Grothendieck's proof because that, like I said, I come from arithmetic geometry, and that's the only proof that's applicable in all characteristics. The ones by Clemens and Riskorn, Griffiths, they would be working over the complex numbers. And Landsman. And I should say later on, there were other proofs by Katz, Wolford, Schmidt, and they would do kind of more general things, but where instead of just allowing the constant local system, they would allow variations of Haas structure or more general vector bundle with connection with regular singularity and things like that. But I won't discuss that. Let me just talk about Grothendieck's proof. So Grothendieck gives two proofs of this result. So the first proof is really striking. It's completely Galois theoretic. It's an abstract statement about Galois representations. And he uses this plus what's known as Néron desingularization to deduce the statement in arbitrary characteristic. So I won't talk about that proof. The second proof he gives uses Hironaka's resolution of singularities. And maybe I'll discuss this more later on, because this will help explain why you might from the Galois theoretic proof, I still find it mysterious. But the geometric proof, the reason is that if you were to look at a family which had semi-stable reduction, if these words mean something to you, then you could explicitly compute it. And in the semi-stable reduction case, it's easy to see that you can just explicitly compute what the action is, and it turns out to be determined by the numerology of the, semi-stable reduction means that it looks like the special fiber is like, if you choose a parameter here, it looks like there's some coordinates in the special fiber so that it's the vanishing of x1 through xk equal t. So special fiber is basically special fiber is a divisor with normal crossings. So that case is much simpler and you can compute it explicitly. Here, of course, the special fiber could be anything. But you can use Hironaka to get to that stage. And that's essentially what Grothendieck does. He uses Hironaka to get to that point. And then so he gives two proofs. That's where resolution of singularities proof. So that second proof goes through semi-stable reduction, more or less. And so this proof, when he did it, of course, was only valid in characteristic 0, because there's no resolutions in characteristic P. But in fact, you don't need resolutions, you only need alterations. So Deligne gave an alternate approach in the late 90s after de Jong's alterations came, wherein even you can do this kind of argument with alteration. But the nice thing is both proofs are very interesting, because Grothendieck showed how to answer Milner's question in the positive using this proof. And you really need this proof. This proof is not enough to deduce this, because it comes from the method of proof, deducing that quasi-nilpotence of the Miller monodromy action on the Miller fiber. And so kind of both proofs are really interesting. They both had significant applications. The other thing is, with this proof, you can do a little better. So you could ask, can we say something about this n and k? Okay. What are they? Where are they coming from? So it turns out that the k is always less than or equal to I plus 1, the level of cohomology. Okay, so I'm looking at the action on the ith cohomology, because the stocks of this are the ith cohomology. So that's called the usual people call that the exponent of nilpotence. It turns out to be bounded by I plus 1. And this is really important because, for instance, it means that if you're looking at H1 of an abelian variety, it's bounded by 2. And Grothendieck used this to give the first proof of semi-stable reduction for abelian varieties. This is what he does in SGA7. So in fact, it's equivalent. He shows that it's equivalent. If this is less than or equal to 2, then the semi-abelian variety has semi-stable reduction. He showed that it's an if and only if. It's a generalization of like what Sayre and Tate proved, which said that something has good reduction if and only if the Galois action is unramified. But so both proofs are interesting, and it's okay. So you might say, well, okay, it was only valid in characteristic 0, but the thing is that he only uses it for H1. And for H1, you only need to look at Jacobians of curves. And for curves in characteristic P and surfaces, you're still okay. You have resolutions. For arithmetic surfaces, resolutions was known. Yeah. It's a curve over DVR, so it's technically a surface, rule dimension 2. Bianca proved resolutions in characteristic P. So actually, the proof is unconditional for semi-stable reduction of abelian varieties. Nowadays, people go the other way. I mean, later on, of course, there was an independent proof of semi-stable reduction of curves. Then you can go back, and Artin showed how you could use that to go back and prove semi-stable reduction for abelian varieties. So I mean, now there's multiple proofs, but this is the way he does it. Yeah. It turns out that actually you can even get a better bound if you're. In fact, it's bounded by the Hodge-Coniveau, if you know what that means, and that's the improvement that Katz obtained. So, but that is of course a Hodge theoretic statement and only valid over the complex numbers. I don't think any analog of that is known in characteristic P. Okay, so the question I wanted to sort of that we start. Yeah, I should have said this. This is all joint work with Madhav Nori. So we were studying actually kind of a different problem, but which if there's time, I will mention it towards the end. But yeah, so you could of course now ask, well, this is for constant sheaves. What about arbitrary sheaves? You know, what happens? And for arbitrary sheaves, it's not even clear what to hope for because, you know, I mean, local systems can have all sorts of local monodromy. So for instance, if I just took GM, right? If I just look at the punctured plane, well, what are rank 1 local systems? So I said that they were classified by representation of the fundamental group, which in this case is Z. So they're just characters, they're determined by characters of Z. So what is there? They're just multiplication, eigenvalue. So what are every complex number will give you a character. And that complex number will be the corresponding eigenvalue because you're just multiplying by that number. So even any complex number, there's a local system corresponding to that complex number. And the eigenvalue, the local eigenvalue here is lambda. So of course, you can get everything, not just roots of unity. So the question is, what could you say in general? If I start with an arbitrary constructible sheaf, what can you say about maybe, is there some relation between eigenvalues of the thing downstairs and the thing upstairs? And so that's what I want to sort of explain. And so I need to introduce some notation. Okay, so I want to think about things a little bit more algebraically, and I'll explain why a little bit later on. But so far I've been looking at maps from disks, but that's equivalent to saying that I have a map from the spectrum of the ring of Laurent convergent series. So convergent Laurent power series. Okay. But anyway, you know what I mean. So I can look at convergent series around the origin punctured, and giving a map. If I have a map of schemes over C of this form, it gives you a map from a disk. That's not that hard to see because what does it mean to give a map like this? Well, in any case, I can assume X is affine because this is just a point. It's going to land in some affine, and this is finite type. So this is just some finally generated algebra over C. So, you know, it's given by something like C of X1 to Xn and maybe some polynomials. And giving such a map is equivalent to giving yourself a bunch of power series that satisfy these equations, or Laurent power series. And each of those power series will have some radius of convergence. And so I take the smallest one, and then I will actually get a map from the disk to X. It's giving a map like this is again giving a bunch of, you know, series that that satisfy these equations. So these two things are equivalent, giving a map from a punctured disk to S or giving a map of schemes like this. I prefer to think this way because this, yeah, and well, so for me, an algebraic loop on X by definition is just a set of maps like this. It's a set of maps from spec P to X. And as I said, if I give you an algebraic loop, I can associate to it a map from a small enough punctured disk to X. So in particular, if I have a constructible sheaf on X, I can pull this back along this map to the punctured disk. And this is a constructible sheaf. So again, if up to shrinking this disk, I can assume I get a local system on the punctured disk. Okay. So any such map will give me a map from the punctured disk. And for a small enough disk, this will be a local system on this punctured disk. And so again, I can talk about its monodromy. By that, I just mean eigenvalues of the generator of the fundamental group of D. And I'll denote that set of eigenvalues by SP gamma. I mean, it's the spectrum of that operator acting on F. Okay. So given any algebraic loop, I can talk about, this is what I mean by local monodromy of the constructible sheaf. I can talk about its local monodromy along that loop. Okay. This is some set of complex numbers. And so this is just setting up some notation. So, and so the total monodromy in a sense will be the union of all of these. Right? And so I'll call that the boundary. So this BSP is for the boundary spectrum. So the boundary spectrum of F will just be the union of the spectra over all algebraic loops. Okay. So it turns out that with this notation, so for instance, let me just give an example. If you started with a constant local system, like suppose I just took C on X, what do you get? You get nothing. It's just 1, right? Because C, if I pull it back, pulling back C along such a map to D cross, I'll just get C again. It's the trivial local system on D cross, which has trivial monodromy 1. So in this case, the spectrum over any algebraic loop of this sheaf is just 1, and the boundary spectrum of the constant sheaf is 1. In fact, it's true for any local system. Okay. But of course, the question that I'm interested in is what happens to boundary monodromy under a push forward?
I think you said this and I just missed it. The spectrum thing, that's just the eigenvalues of the monodromy action.
Yes, yeah, that's right.
There's like 1 because you have like a punctured disk roughly, and you just have the 1.
Yeah, I made a choice. I'm always choosing the canonical generator, and that means counterclockwise loop. Okay. It makes a difference. Well, I mean, I'll get the negative if I go the other way, and it makes a difference. So I made a choice. I'm just going to choose this one. Yeah. Usually, I mean, that's usually what people choose. I mean, it's just dictated by I don't know, history, I guess. But that, yeah. So when I say canonical generator, I mean that one in the punctured disk. Yeah. And I'm always taking the monodromy of that. Yeah. You have to make a choice. Otherwise, if I allow arbitrary things, because I'm going to make a statement about how it's pushing forward, and I'm going to compare monodromy here and here. So now suppose I'm given a morphism of varieties. And now I don't care what X and I'm not assuming anything about the dimensions of X and Y. I have some morphism of varieties and I have a constructible sheaf up here. So it turns out, this is the theorem that this is sort of the, well, one way of generalizing the local monodromy theorems. It will, of course, imply that. So suppose I have this setup and I fix some algebraic loop on the base. So then the theorem is that there exists a finite set of algebraic loops, let's say, upstairs, such that they map to the loop downstairs up to a power. So what I mean by that is that such that if I take such a loop in M, then there exists an N, so that if I have a loop up here, I can compose it and I get a loop down here. So I can look at, if I compose this loop, I want it to lie above the loop I started on the base, but up to a power. So it's gamma to the n for some n. So there's a finite set of loops above this fixed loop here. So finite set of loops and an integer r, so that the spectrum of the algebraic loop of the push forward, and I'm going to be a little vague here. You can take any I here if you want. And here you can take pi lower star, but you can also take pi lower shriek if you know what that means. Fine. If it doesn't, if you don't, it doesn't matter. Derived image with compact support. But let me just stick with star for a second. Of f is contained in the union over all loops in this finite set M of the spectra of the, well, let me write it this way. So the set of lambda such that the rth power of lambda is a spectrum of this thing. And the sheaf upstairs. Okay. Okay. It looks technical, but let me just suppose we're actually over disk. Suppose the base is just the disk, and we're just looking at that canonical loop on the disk. So, and suppose I have a constant sheaf upstairs. If I have a constant sheaf upstairs, then these are all just one, as I remarked over there. So all I'm saying is that the eigenvalues downstairs are in the set of things whose rth power is 1. Which is just saying that the eigenvalues are all roots of unity. So this recovers the local monodromy theorem. It's a generalization of the local monodromy theorem for arbitrary sheaves. And you can also make a statement, at least if dimension is 1, if the dimension of the base is 1, you can combine this and it turns out that the full spectrum of the thing downstairs will be contained in the spectrum upstairs. This is just my notation that this just means like rth roots of the things in here, okay? So all I mean by this is that something is an eigenvalue here if its rth power is in here, okay? That makes sense?
Still trying to parse the statement.
Yeah.
So M, I like have this intuition that M should be the type, like should be loops upstairs that sort of map down to gamma.
Yeah.
Did you say that somewhere?
Yes, up to a power. So there's a finite set of loops upstairs so that some power, so such that if I compose that loop with this map, now I get a loop downstairs.
Mm-hmm.
That loop downstairs is some power, some fixed power of the loop that I had downstairs.
Yeah.
So it doesn't quite map to it, but up to a power.
Yeah. And could it be that M is the empty set?
No. So I mean, yeah, it better not. I mean, not really, because I'm saying that because this, well, I don't know. I depend. Okay, let's assume f is not 0. Then I don't know what is the eigenvalue of 0. Is it everything or empty? I don't know. But otherwise, this is not empty.
Mm-hmm.
So this side can't be empty.
I see. So F is like the things upstairs that map down to some power of gamma, but it could, maybe we have to add more things to it. At least in the statement.
Again?
So I'm like parsing the statement. I'm like, I think I'm having quantifier trouble.
Yeah.
You're saying if M is bigger, then it's easy to satisfy like condition 1 because you have more things on the right. Is that right?
No, I mean, are you asking why I'm insisting on a finite set M?
Yeah.
Yeah, it's because I want to make, at the end of the day, I want to make an independent statement. So this statement doesn't depend on the loop at all. It's the union of all algebraic loops. And if I don't have a finite set, then this R can vary for every single gamma. I want this R to be uniform in gamma. Because I want a fixed R that will work for the full boundary spectrum for any loop. Loop by loop, yeah. I mean,
But you want R to be uniform in gamma prime.
Yeah, so, okay, so this is the statement for a fixed loop.
Yeah.
Downstairs. Now I could ask, what is the full spectrum, which is the union of the spectra of all loops downstairs?
Mhm.
Okay, and I want to say that those eigenvalues are still like roots of unity for some fixed R.
Yeah,
Okay? The first statement gives me one R for each gamma.
yeah,
Now, in principle, if I go over everything, that for each, as the gamma downstairs varies, the R, which in principle depends on the gamma, could be unbounded.
yeah, with the gamma prime downstairs.
Well, yeah, I'm calling gamma the thing downstairs and gamma prime the thing
Oh.
downstairs. Yeah,
Yeah,
the loop downstairs. Yeah.
Yeah.
Right. Yeah. So it's important to have some kind of finite number of loops upstairs.
explain it.
There is also a statement in higher dimension, but I don't want to talk about it. It's a little bit more technical to state. Okay, so let me, so I have about 15 minutes. Maybe I'll just make a couple of remarks. So this theorem was known before in a special situation, namely, maybe I will just say there was an intermediate result. So it wasn't like that result and then this, though not too far off. I mean, Kashiwara proved something intermediate a while ago. And then it was generalized. Well, maybe modified rather, not generalized, by Moriko Saito in the setting of mixed Hodge modules. But what Kashiwara showed was that if you started with a quasi-unipotent sheaf upstairs, then its direct image is quasi-unipotent. And so the way he defines in the language that I've set up, this is not the way, he doesn't use this kind of language, but this is more convenient language for us. In this language, quasi-unipotent just means that this consists of roots of unity. Okay. And so what he shows is that if you started with something upstairs where all these spectra are just consist of roots of unity, then the direct image also consists, its spectra also consist of roots of unity. So so that was and that's important. Yeah. So he showed that direct images of quasi-unipotent constructible. Okay, so in the last 10 minutes, I want to explain kind of a related result, which, so you might say, well, okay, what is this kind of more general result useful for? It has something to do with, so I'm going to set up a specific, yeah, I'll just give a couple of examples. Maybe that does. Let me just do a couple of examples. So maybe the first remark I want to make is much of what I said goes through in the setting of R modules. Okay. And so what I mean by that is I took constructible sheaves of complex vector spaces. Or I mean, I could have took constructible sheaves of K vector spaces for any field K or algebraically closed field K. The statement still makes sense. And there's no, I just used existence of eigenvalues. There's nothing. I mean, all the statements make sense and the proofs go through. The same exact result is true without any modification. But I could work more generally with constructible sheaves of R modules, where R is some commutative Noetherian ring for technical reasons of finite homological dimension. But in that case, it's not even clear what to write here anymore, because what is an eigenvalue and what is a spectrum and so on. So you can still discuss something in that case, namely, if I have a constructible sheaf of R modules, well, I still have this map, let's say from the punctured disk to X, and the pullback is a locally constant sheaf of R modules on the punctured disk. Okay, and so it's actually a constant sheaf of R modules. And so I would like to talk about eigenvalues, but I mean, I'm working over a ring. So what does it mean? And also, not only over a ring, I don't necessarily have a free module. Okay, if I had a free module, let's just suppose that this turned out to be a free R module. Okay, then I could go to the fraction field and I could take its algebraic closure, and then I could talk about eigenvalues, and I could repeat the statements, okay? But I don't really want to do that. I actually want to work over R. So the algebraic geometer's way of doing this is to just say that this is a R module, but in fact, we want to view it as an R of T module. So T is an element of pi1 is the canonical generator. So in fact, this thing is, because it's a representation of that fundamental group in R modules. So this is a R of T module, just by definition. Okay. If I have a representation of pi1 of D cross in automorphisms of R on some R module, I actually have an R of T module. Okay. And
R is any ring, or is there some
any commutative Noetherian ring with finite homological dimension? Yeah. The example I'm going to do is the Laurent polynomial ring. So if you want, you can just assume this. This is the example I'm going to do in a second. I don't know. I mean, it's the usual way of doing the one way to do the Jordan canonical form is to view it as an R of T module. That's all I'm doing. Okay. But so I have a module over this, and I can look at its support, which is some closed subscheme. I mean the schematic support. It's some closed subscheme of the affine line, and that's the appropriate generalization of the spectrum. Okay, because the corresponding ideal is the annihilator of this module. If I'm working over a field, this is a PID, and it's generated by the minimal polynomial. So that's by definition how you get eigenvalues. So the appropriate statement will be about this. And I don't want to go through it because I'm running out of time, but you can make a similar statement where instead of using spectra, you use this notion of spectrum. By that, I just mean this closed subscheme of A1R. And you can show that this closed subscheme is contained in a bunch of other closed subschemes that come from loops upstairs. Okay, so that's kind of an appropriate generalization. But why one cared about this was because of some explicit examples that come out of maybe arithmetic geometry and maybe geometric group theory. So I'll end with maybe just two examples. I mean, this was the kind of setting why we were interested in this kind of result in the first place. This is what motivated it. Okay. So suppose I have a semi-abelian variety. If you want, you can just assume it's a torus. Some power of C stars. Okay. Or if you prefer, you can assume it's an abelian variety, but I'm going to allow a semi-abelian. It just means an extension of an abelian variety by a torus. So, okay. So it's a mild generalization. So on this, there's a canonical local system. You think of it as a universal local system. So pi1 of A, acts on itself. So in fact, Z pi1, the group ring, is a module over itself in the canonical way. And Z pi1 modules are equivalent to, I already said, local systems of modules. So this, in fact, gives rise to a local system on A. It's the local system, it's a local system of Z pi1 A modules whose, let me choose a base point just for a second. The base point will be the identity element. Okay. This is the algebraic group, so I can just take the identity. And the stock of this at a point Y is just Z pi1, the group ring on the homotopy classes of maps from the identity to that point. This is a kind of a standard local system. Another way to think about it is if you want, if I take the universal cover, if I just take pi lower streak of the constant sheaf here, it is exactly this local system. Okay, that's a more geometric way of constructing it. But this local system is a local system of R modules where R is this group ring. But what is this group ring? Well, topologically, these are tori. And so, the fundamental group is just a free abelian group on some number of generators, depends on the rank of the torus. And so it's exactly a Laurent polynomial ring in more than one variable. But if it was GM, it would just be this. Okay. So this is an example of a local, this is an example of this kind of object, a local system of modules over a Laurent polynomial ring, okay, of R modules. Okay. So you can, so these kinds of, I mean, geometrically, geometrically, this thing parameterized, this is a moduli of local systems. You can think of it in that way. Okay. If I were to, maybe I'll just make one remark. I mean, where is this really coming from? If you look at this local system, let me just do it for the torus, right? It's a local system of ZTT inverse modules. And now suppose I take some maximal ideal in here, and well, this is a local system of ZTT inverse modules, so certainly I can tensor it with, let me just write, so this is my R state, so R mod M, I mean over R, right? Section by section I can do this. So now I have a local system of R mod M modules. Well, let me take C now, just let me work over C for a second, tensor everything with C. So I have a local system of complex vector spaces. And that local system is just a local system corresponding to whatever, this is generated by some polynomial, whatever the zeros were. So the eigenvalues are those. So this is putting, earlier I wrote down these local systems L sub lambda. This is putting together all of those local systems together into one big system. Okay. Kind of like a moduli version of it. Okay. So you could play the same game in this setting, namely, suppose I have a scheme over some base and I have a map from this to some family of abelian schemes over S. So there's a family's version of this local system on this abelian scheme, and I could pull this back to X along this map. Let me call this map F, this family's version, and I could look at the cohomologies of the fibers of this. Again, if I restrict to a small enough disk around here, this thing will form a local system on that disk as I vary the S in that disk. And it's a local system of modules over a ring like this. And you could ask what its monodromy is. So you get a representation of the fundamental group of this on this. And the result in this case would say that if you go through it, I can explain this maybe later on, but let's me assume it's free for a second. It can be free for depending on what X you start with, just because I don't want to deal with torsion for a second, just to simplify things. Then this is a free module, and I could ask then I don't really have to deal with supports. I can actually talk about eigenvalues in the algebraic closure. So I can look at the eigenvalues of T acting on this in the algebraic closure of the fraction field of a ring like this. And it turns out that they are some powers of them. So they're sitting in the algebraic closure of the fraction field of something like this. And it turns out that they're all powers of monomials. So what I mean by that is the eigenvalues look like T1. So the eigenvalues satisfy the property that some power is equal to maybe T1, depending on how many variables I have, raised to the N1 TK. So they're monomials in the generators. Okay. And this follows because the theorem says that the eigenvalues some power are eigenvalues upstairs. And so I really just have to compute the eigenvalues of this global local system on A. And if you do that, you just get monomials. So that's where, so some power will be such a monomial. That's kind of what you get. And so you might say, well, okay, what's the point of looking at like something like this? And I think I'm probably out of time, but maybe I will just say in words, there are lots of representations that come from like arithmetic geometry, like variations of polylogarithms and things like that are in this framework. But then there's also representations of a different flavor that come from geometric topology, like the bureau representation. The bureau representation is a representation of the braid group on GLN minus 1 of ZTT inverse. This is a representation that is studied by many people in say topology or because it realizes the Alexander polynomial of a knot. So if the closure of a knot is a braid, then if I look at the image of this braid in here, then from this you can determine the Alexander polynomial of a knot. But anyway, one can show that the bureau representation is a monodromy representation in this sense. There's a specific S and a specific X and a specific A, for which if you do this construction, you'll get the bureau representation. It is not the way it's defined in the literature. The topologists do it very differently. But anyway, I'll stop here. Yeah.
Any questions for Deepam?
Last thing you said, is it defined, you said it's not defined, it's representation of the braid group. You've written that.
I did write it down.
You wrote it up.
It's the kind of thing that you never want to really claim. I mean, so I'm writing a survey paper where I decided that it's better to write as a survey paper. It's bound to piss people off, right? Because there are a lot of representations that geometric group theorists look at, like the bureau representation and generalizations, like the Gassner representation or the Lawrence representation. I asked this to group, so they write it out very explicitly. I mean, Bureau discovered this representation, it came from physics, like back in 19. So he would just write down generators of the braid group, and he would tell you exact matrices. That's how it was written down. And then people found connections with knot theory and same thing with Gassner representations and the Lawrence representations. At some point, we realized that, maybe Madhav really, that they can all be written as monodromy representations. It's not in the literature, that something very close it is, but not quite. And maybe people just don't care to realize it algebra geometrically. But for me, it was important because it means that there is a Galois action, and you don't see that if you do it the way, because the reason I say there's a Galois action is because, maybe I don't want to hold up people. I can explain how it's constructed. The S here is the moduli space of separable polynomials of degree n. Right? So polynomials with n distinct roots. That's the moduli space. And the X will be
one variable, right?
In one variable. Yeah, just the bureau. Yeah. So you're looking at, so so that's the way I think about it. The way the topologists would think about it is that this is the configuration space of n distinct points. It's the same, but there is benefit to doing. I'm just viewing the same topological space a little bit differently. Okay. But if then you can write down, so the A will just, so P is that space. The A will just be the split family, like the most easiest example. So this is trivially a semi-abelian scheme. It's just a torus. It's a split torus family over P. It's a family of tori, and it's a constant family. And X will be a subset of A1 cross GM cross P, which is the set of points X, Y, and P, so that P of X equals Y. This is a closed subvariety of this. And there's a natural map from this X to here, which just sends such a point to the value of P in the first coordinate, the Y, and in the second coordinate, the P. And you get this. And if you go through this, and if you look at the H1, it's really H1. I mean, if you do cohomology, you'll get the dual. So you'll get the conjugate representation. So if you really want the exact bureau representation, you have to take the homology. But anyway, you take H1 of this family at a general P as P varies, and you can show that this is a fiber bundle. That's not that hard. Smooth fibration. And with coefficients in this local system that I wrote down for this semi-abelian variety. This will be a ZTT inverse module because that's the fundamental group here. You can show that this homology group as a ZTT inverse module is free of rank n-1, and you actually get the Bureau representation. This is the family that realizes the Bureau representation. Yeah, and there's a similar, but you see when I write it this way, this is defined over any field. I didn't have to use the complex numbers. It's defined over a finite field. And instead of this, I would take Étale cohomology. You can still make sense of this. And so for me, it's like an arithmetic object. It's an example of what we call gamma motive, but you know, it's not quite the way that the geometric group theorists look at it, but it's not too bad. But the one thing I want to know, if there are any topologists or geometric group theorists in here, is there a, because I just don't know any of this, is there a representation that geometric group theorists are interested in? Outside the Lawrence, Kramer, the Bureau, and the Gassner, because I don't know how I know how to deal with those. For which one might wonder over large rings like this, for which one might wonder if they come from geometry. Yeah. Algebraic geometers don't tend to look at representations over large rings like this. You usually work with representations in finite dimensional vector spaces. But these kind of representations show up a lot in certainly geometric topology.
Any other questions? Your speaker again.